In this problem, we're looking to find an approximation or a pair of approximations for the integral from 1 to 5 of the square root of x squared plus 1 dx. This is a definite integral, and our function, notice here, is it's graphed over here. It's positive on this interval, so this value that we're calculating here would represent the area between the x-axis and this function between the x values of 1 and 5. So if I draw in a couple of lines here, we can visualize this easier. This is in between 1 and 5 between the x-axis and the function. So it's that little region right in there. I'll highlight it in yellow. We're trying to find the area of this region right here. All right. And you might be tempted to find the area exactly using the fundamental theorem of calculus, but one of the limitations to the fundamental theorem of calculus is that it only works if you can anti-differentiate the function. And you might give that a try, but this is not a substitution problem. Having that square, or the square root with the x squared plus 1 inside turns out to cause a challenge here. So we're not expected to find it exactly. We're going to simply approximate it, and the way we're going to do that is to use a technique called Riemann sums. Riemann was a mathematician that came up with an approach for approximating these areas, and we're going to use the simplest of those, which is areas of rectangles. In practice, you'd probably want to use a lot more than 2 rectangles, but we can illustrate that we understand the process by simply doing 2. Let's see, we're working from x equal 1 to x equal 5, and we want to fit 2 rectangles in here side by side. So this width is 4, and we want 2 of them in there. Each one would be 2 wide. So the first one will go from 1 over to 3. So I'm going to draw in that edge of the rectangle. And the next one would go from 3 to 5. So I've cut this vertically into 2 strips now. One from 1 to 3 and one from 1 to 5. And I want to approximate the areas of those 2. We're going to do that twice, once with using a lower sum, the other with the upper sum. And the lower sum means what we're going to do is find areas of rectangles that fit below the function. We want the tallest rectangle that fits under this. Since this function is increasing on this interval, the low end is the left end. So the tallest rectangle we can use and guarantee that it fits under the function is that one right there. When I get to the next interval, I can use a taller rectangle. I don't have to use that same height. I can move all the way up, but again, the function eventually stops me, so I draw a horizontal line right at that y value. And so our goal now is to figure out the area of these 2 rectangles. The area of these 2 rectangles added together will be less than the overall area, so we're finding out the value that goes right here, and that's called the lower sum, lower Riemann sum. And so all I need to do here is add up the area of 2 rectangles. Areas of rectangles are width times height, so the form of my work here is going to be width times height plus width times height, just twice. And now what I got to do is find the 4 numbers I'm working with and plug them in. The widths on both of these, I can see just from observation here, are both going to be 2. They go from x values 1 to 3, which is a gap of 2, and then 3 to 5. The y values are the only other dimension I need. And so we just, looking at the graph as a guide here, we can see that the height of the first rectangle is going to be the height of the vertical line at x equal 1. It bounded from the x-axis up to this point right here. And you might be tempted to use the function's graph here to try and read it off. The graph paper is just not fine enough. If you want a good approximation, you don't want to really eyeball this. You want to calculate the length of that vertical line there. But if you think about it, the length of that line is the height of the function at x value 1. So the y value dimension here is going to be the function evaluated at x value 1. And since I have the rule for that, I can simply plug in x equal 1. I'll get 1 squared plus 1 under the root, which is the square root of 2. So the height of that first rectangle is exactly square root of 2. All right. And now we just repeat this process on the second interval. Over here, the height of the rectangle that I'm going to use is that height right there, which is the y value on the graph that corresponds to x value 3. So the y value on that piece is going to be f at 3, which is the square root of 3 squared plus 1, which is the square root of 10. So that second height is square root of 10. So the area of the first rectangle is 2 root 2, the second rectangle is 2 root 10, and overall, see, I'll grab my calculator, that's going to end up being right around 9.153. And so that is the lower bound on that. We know that the area we're really looking for, the area A, is somewhat more than 9.153, and graphically we can see it's this much more plus this much more. All right. But that gives us a lower estimate. For the upper estimate, we're basically going to do the same thing, except when we draw in our rectangles, we want the rectangles to contain all of the yellow area. So on this, still going to use two rectangles, so the widths are going to remain the same. So as I start to draw these calculations out, again I'm going to have two rectangles, and the widths on the rectangles are still going to be 2, but the heights may change. The height of the first rectangle, if I want to make sure I capture all of the area, on this first interval I'm going to have to go this high. Right? That large rectangle going from the x-axis all the way up to there contains all of the yellow area on that interval. And on the next interval, I want to go up to that height. So it's this high and this high are the two heights that I'm using for the upper sum. And so again, I want to go back into here and fill in my y values. And part of this work we've already done. If we notice, the height of this first rectangle here is the y value that corresponds to x value 3, and we've already figured that to be square root of 10. The only thing I need now is the height of this new side that we've added in, and so I'll calculate the y value there. But again, that's the y value at x value 5. So I can use the functions rule to calculate that, square root of 5 squared plus 1, or square root of 26. And so square root of 26 is the value, that dimension of the larger rectangle, the upper rectangle, for the interval from 3 to 5. So again, grabbing the calculator, I can figure out the total area represented by those two large rectangles, and this comes out to be about 16.523. All right. So the upper bound on the area is 16.523. Again, this isn't a very tight estimate, but it does tell me that the area, the yellow shaded region, the area represented by the integral from 1 to 5 of this function, is somewhere between 9.153 and 16.523. If I wanted a better estimate, I'd go back and use more rectangles. Cut this into narrower strips. The approach to finding the area would be identical, and the more rectangles I use, the tighter these two are going to get. In other words, they're going to move toward each other, and they would have to come together eventually at A, although it may take infinitely many rectangles to do it. But you can get as good approximation as you like by increasing the number of rectangles. So that's it for this one.